So here we have basically a 10 megahertz square wave. Why do I show this case? It's because from the beginning we targeted this as the target spec that we want to achieve.
10 megahertz.
Exactly. So I think for personal usage or usage on the road, what you need, or even 90% of professional work in the lab, basically 100 megahertz samples are sufficient for most of the work.
Okay.
Here example is a 10 megahertz square wave, which you can see nicely visualized. What you can also see that even this signal is sampled 100 times per second, 100 million times per second, it still looks quite smooth, and that's because we implemented a lot of features in there. There's sync triggering, which really makes sure that the triggering is exactly where it's expected to be. We also have equivalent time sampling, which, if, for example, if you turn it off, you get an impression of what it would look like if it would be not there.
Okay.
So if you enable it, you see basically so this is the default mode, and you can see that the square wave is coming through nicely. So it's really, there's actually quite a lot of optimizations basically in there, which are not there in standard scopes having this frequency.
Yep.
Okay. So the next thing I'd like to show is where we, for example, use this logic analyzer part to visualize a signal generated by a development board.
Okay.
We can do.
Yeah. So we've got rid of the generator, and a new thing has appeared on the table, Riemer, a genuine laptop. So far we have seen a tablet doing the controls, and now it's a laptop. And there's something connected over there.
Yes, exactly. So for this part, I've connected a evaluation model for Texas Instruments temperature sensor.
Okay.
So it's basically a simple board containing 8 temperature sensors, which are I2C controllable.
I2C, serial protocol.
Exactly. So it's a serial protocol, and we're going to hook it up. Well, I hooked it already up to the logic analyzer ports, and the idea is that the bits are going to be captured by the SmartScope, and that we're going to try to read up the temperature from the sensor.
Using a laptop.
Exactly. So on the left side, basically, you see the SmartScope software on the two top sides. So you see the 8 logic analyzer channels. On the right side, you have the evaluation software from Texas Instruments, which allows me just to read out the temperatures. So what I can see here on the left side is that I've set up for the trigger on a rising edge of channel 0. So now if I'm going to generate an I2C stream, so I'm going to read out temperature H. So you see actually the 2 data streams on your screen, and now you can start counting edges and see which bit is high, which is low, and you can try to decode the I2C. But inside the SmartScope software contains also a couple of decoders of the most standard protocols. Everything comes for free included, of course. Yeah.
Can you mention a few protocols?
Yes, let me see what we have. So we have
I2C.
Yes, we have SPI 3 and 4 wire. You have I2C, I2S, UART, and RS232.
Yeah.
So if we add a I2C decoder to our captured data, you see that automatically it initializes itself, and it selects the 2 channels as input data. And you can see is that it has already decoded information, so it's a standard I2C communication. So the chip address is a 77 hexadecimal, and the value is 1B. Of course, you can change the radix to whatever you want, for example, to decimal numbers, and then you can see that so the chip number is 119, and it reads out as 27 degrees.
So if you had an I2C device which is unknown or secret or whatever, you would be able to find its name and communication.
Yes, of course. Then still you would need to have the data sheet to translate the data, but of course all the data you have there is here decoded for you, so you don't need to see actually which edge aligns to which bit. Okay. So this is for the I2C part. I have another small demo where I can hook up the output, digital output, generate an SPI signal, and then also decode it by the software.
Let's do that.
Yes. So it's fairly simple to do because I just need to hook up all of my signals here to digital outputs of the scope, which is done like this. And next, you can simply enable the digital generator, which will for now not produce too much because we haven't yet uploaded the file. I made a file in Excel which contains all of the bits to toggle for the SPI communication. Okay. So you can just upload it from your local disk, or from Dropbox, which runs on my local disk.
Uploading.
So it's been uploaded.
Processing. Yeah.
Exactly. And there you see that there's some communication on the channel. Let me see. Yep, so we have 2 channels, which is obviously not enough for SPI, which is because I connected to the wrong channel.
Here we go.
Here you have 3 channels. So also in Windows you have touchscreen support, of course. And here you have a fairly busy communication. You can, if you want, to simply stop the acquisition, after which all the information is transferred to your PC.
Kind of freezes and make a snapshot of what's happening.
Exactly, yeah. And then you can simply add a decoder. So the SPI decoder, there it is.
Yeah.
Let's zoom in a little bit on the data.
Beautiful.
You might need to set the right channels. So the chip select signal is obviously the red one.
Yeah.
Then the clock is the fastest one, it is the first channel, and this one is the next. And there you have it, it's completely decoded.
Yeah.
So then again, you
all the words in blue in the box.
Exactly. So here also the information conveyed is in ASCII. So you can, for example, choose to display the information in ASCII. And there's it was made by someone on the forum. So there's actually a message there embedded in in the signal itself. So that shows how easy it is to set up the decoders on the LabNation software.
And now, Riemer, exporting the stuff, you know?
Yes, exporting.
Someone will want to have access to your data.
Yes,
who's in Argentina or whatever.
Obviously. Well, in most cases, if you are debugging, it's not for someone in Argentina, but for yourself.
Yeah, okay.
Since we have a decoder set up here, let's just talk a bit about the decoder. For decoders, you can of course store all of the data to disk. Also for decoders specifically, it's very simple. You can just tap the decoder and put save.
Okay.
And then it will be just a CSV file containing all of the decoded outputs. Additionally, if you want
importing into Excel.
Exactly. Yes. Then you can simply hit the record button, which you can do on the fly. So that means that all of the data that's coming in, all of it is saved in Excel, which can, especially in Excel, result in large files. For example, here we just do it for one data set. Just say, okay, it's not running, so just the last data. Yes, that's fine. And it's also stored there in an Excel file. Then let's open it up. So we go to documents, LabNation, and there we have a whole lot of information.
Incredible.
Which I should have.
Okay, and it will be any one of these.
Yes, typically the last one.
The most recent one.
Yes, exactly. And then you have it basically in Excel. All of the data is just opening up in Excel, and then you can show your signal. It will be too much to simply simply show.
But you know how it is with technicians. As long as they have the numbers, they will be able to do the processing.
So a small check. So let's just insert a small graph there up, and that's a small section of one of the data lines of. So you have it there, all of it in Excel, that you can process any way you want to. Yeah, so one feature we didn't discuss yet is the AWG functionality, so where you can generate signals that you define yourself. So in this setup, I've just connected the AWG output of the scope towards one of the inputs of the analog front end. If you go into the channel, you can see that the AWG by itself comes with a few standard shapes, for example, square waves, sines, and so on, of which you can set the amplitude, offset, and the frequency. But you can, of course, also define your own signal. So you can upload a file from Excel, and then it's really arbitrary which kind of wave you want to generate. So in this case, it's a simple square wave, which is visualized by the front end. Why did I choose a square wave in this case? Is also because I want to show the FFT,
the fast Fourier response.
Exactly.
To that,
exactly. Yes. So in the analog mode, you can also enable the FFT. So it's another window here at the bottom which pops up. And here basically you see the spectral contents of the signal that you see on top. So for a square wave, it's a typical FFT response shown as here below. You can notice that the peaks by themselves are not too fine, they're a little bit coarse, and that's because it's actually this is in real time. So whatever signal you get in analog signal, it is computed immediately in real time to the FFT signal. And since in real time you only have 2,000 samples for each channel, there's 2,000 bins. Now if you stop the scope, you get the full memory, and then of course your spikes become much more fine-grained, and they get much more information in the frequency counts.
Okay.
So this is two more features of the signal generator and the FFT basically, which are there.
Okay. Riemer, finally, we'd like to discuss things that are not hardware, in other words, software.
Yes.
The development, you are talking about software for this instrument, which is open to users.
Yes.
I think that's a hell of a lot of interest in software aspects of your instruments. Tell us a bit about what's
yes. So the whole idea. So the whole idea from the beginning, basically, when did we start this concept? I've been teaching FPGA development in the University of Brussels for 5 years. So I was thinking, okay, it would be ideal if you would have a platform, a cheap platform with FPGA that you can access easily from the PC. And that's exactly the intention from the beginning. We first, of course, had to make an application that works as a user-friendly oscilloscope and logic analyzer, which is working fine for now. So now we're moving on to the next phase, and that is basically opening up a whole framework which allows people to create their own firmware configurations and software for this platform. It's of course not yet finished. We're targeting to have it finished around September, but this is in general the concept. So in the center of the FPGA, in the center of the SmartScope is a powerful FPGA. There's a couple of breakout headers as well, and the idea is that they can implement their own VGL programs. And upload into the SmartScope. For example, if you need to add a PWM part, you just put it there. But then the nice thing is that you typically want is that you can configure it, that you can configure a couple of settings of your module from a PC. So in simple case of a PWM, you want to set a duty cycle. And then you want to use it in a way that you can easily set it up on a PC. So this is the idea that we have. So if you have your own module, you can just upload in the FPGA. And for example, the duty cycle, you can put in the register bank. And this register bank, it will be accessible from the PC, from a tablet, from any host that you can imagine, local or over the internet, also from LabVIEW, also from MATLAB. And so that people can really extend the functionality to their own liking.
Because this is definitely not a black box.
No.
It looks like a black box.
Yes, actually.
But it is not.
Actually, no, it's actually...
It is totally open
it's actually
to developers.
It's a pretty empty box, and it's waiting for people to put more stuff inside.
You are actually inviting people to participate.
To play with it, and also for definitely universities to make this entry into the classroom. It can be used, of course, as an oscilloscope. But it's also going to be an excellent development project for students and for people who want to experiment with FPGAs. But also, of course, if in some cases you have, for example, LabVIEW setup and you want additional FPGA functionality, just attach a SmartScope, add the FPGA configuration you want, and you can really access it, configure it, and read it out from LabVIEW.
Do you help beginners like myself?
Of course, of course. Actually, that's one of my previous passions. Basically, I've written a couple of books basically with tutorials that was more on programming for people really getting into new stuff. And so that's definitely also the idea with this part. We haven't been able to touch it yet because, as I said, making this app actually simply costs a lot of time. And also for this open source platform will also take a lot of time. Not just throwing the source out there because that takes 2 minutes, but it also needs documentation and sample projects and things like that. So that's definitely what we'll be doing in the coming 2-3 months.
Riemer, I think we've seen a lot about your LabNation scope. It has a hell of a lot of power packed in that little black box, and especially the touch screens are most amazing. And also, the ease to set and control your oscilloscope. It's a totally difference from the old days when you had to turn your controls and watch the CRT screen.
That was the idea from the beginning.
Riemer,
okay,
you're the show, man.
Yeah.
Thanks very much.
Thanks a lot. Okay, bye.